We're now launching into momentum and impulse in that unit there. So momentum is mass times velocity. It has this odd parallel with inertia. The more massive you are, the faster you are moving, the greater your momentum. Now, there isn't a word definition, so to speak, with momentum. It's mass times velocity, where inertia is the property of an object to obey Newton's first law. An object at rest tends to stay at rest, and an object in motion tends to stay in motion. And those two are parallel, but not exactly the same, because you can have a lot of inertia while at rest and zero momentum. Units, kilogram meters divided by seconds, or Newton seconds in S there. Now, in a collision, momentum is neither created nor destroyed. And I should say not just in any collision, I should say here in a closed system, meaning that there isn't anything else affecting it. For example, here, whenever we actually look up at an explosion here, I've got, a little bomb maybe from Mario, and all the pieces go different ways. Momentum, though, is going to be conserved in this closed system. Specifically, the momentum before the explosion is zero, and if you add up the momentum of all the different pieces going different directions, it's going to be still zero. And if you had a whole bunch of particles all over the place, and there were internal forces causing one particle to go to the left, well, Newton's third law says for every action, there's an equal and opposite reaction. So the particle that did the pushing would go to the right, and the net momentum would still be exactly the same. That's kind of what happens here in the explosion. The explosion forces one particle to the left, another particle to the right, and because of that, the net momentum is still zero. By the way, the center of mass, which we're going to talk about later, stays in the exact same spot, also the entire time. Now, a very useful concept that kind of comes from this is the concept of impulse. Impulse, you'll sometimes see it used with a capital J here, because I ends up getting used for current, electrical current. Now, impulse, change in an object's momentum due to a net force being applied to it. It's force times time if the force is constant. If the force isn't constant, it's the integral of F dt, or the force times the force dt. Let's see here. It's also the change in momentum. So if you set these two equal together, you get force times time equals the change in momentum, because this idea of impulse really isn't overly useful, but force, time, and change in momentum, now that is. That should make some logical sense to you. If you push on an object for an amount of time, you cause a change in momentum. Specifically, you're going to cause it to speed up or slow down. Oftentimes, whenever you push on an object, you don't cause it to lose mass, so the change in momentum will come from a change in velocity, momentum mass times velocity there. So you'll have a change in velocity. Three different types of collisions we'll deal with. Hopefully you remember these from middle school. Elastic is where objects bounce off of each other, and if it's perfectly elastic, then all kinetic energy is conserved. We don't lose any energy in a perfectly elastic collision. Now, those are unbelievably rare. The best parallels you could have maybe are pool balls. These objects aren't allowed to deform at all. You need magnets or something else to make it perfectly elastic. Inelastic collision, there is energy loss. Generally, things deform, and if it's perfectly inelastic, they will actually completely stick together. They won't ever separate. An explosion is where objects are stuck together, and then whether it's the two objects push off from each other, or there's a chemical reaction, you get a whole bunch of pieces, or if it's a spring or magnets or something else cause things to launch off, so they then separate. Equations for each of those you'll see over here. I would like to point out that the other bottom equations are really a derivation of the elastic one. The elastic is very basic. It's momentum of the first object before the collision, momentum of the second object before the collision equals the momentum of the two objects added together afterwards. And then these other two should make logical sense from that. If the objects are going to stick together afterwards, well, we just add the masses, and if they're stuck together, they have the same velocity. So they're like one object now on the final side. And if the objects were at rest in an explosion beforehand, well, here all of your initial velocities become zero, leaving you only with finals. So we're able to move this guy to the other side, subtract him over, and get this equation. Now, the area under a force-time graph is the object's impulse, which is the change in momentum. So area under a force-time graph, force times time is impulse. Area under a force-time graph, think about the integral, is the change in momentum. So if I have a very simple-looking graph, for example, like this one, all I need to do is calculate the area of the two sections. And you can see I can come out just from those two sections with a change in momentum of 35 kilogram meters per second. And if you know the mass, which I gave you up here, 5 kilograms, and you're told the initial velocity, let's say the initial velocity, let's make VI equal to 0, or V naught, I believe is what we are using right now, equal to 0. If you know those two things, then you can easily calculate what the final velocity is. Now, what about those times where the force isn't constant, though, or it doesn't change in a nice, easy way that can be shown on a graph? Instead, you're given an equation. Let's say the force changes according to time, negative 3x cubed plus 15x squared, and that graph looks something like this. You've got to get the area under the curve. Well, the area under the curve here, change in momentum, is done by taking the integral of it. So I'm looking for the change in momentum between 0 and, let's say, 5 seconds here. Again, I would just simply take the integral, which then I did, and now we need to actually substitute in. So it looks like, again, with 2 sig figs, 160 kilogram meters per second for that problem where I'm taking the integral because it was a non-constant force and they gave me the equation. Now, obviously, if you're looking for the velocity, you go through the exact same process. You know the change in momentum, and if you know the initial velocity, let's set the initial velocity at 0 again, just to make life easy, and solve for the final velocity. How fast does this object end up going? And I end up with a final velocity of 31 meters per second. You do have to note, even after you get the change in momentum, right? The change in momentum is great, but that's a change in momentum. It could have been starting out with some higher momentum if the initial velocity wasn't 0. So you do have to know the initial velocity. Obviously, you have to know the mass to then be able to calculate the final velocity. Now, let's work one other little very simple problem here. I've got a car. It hits a tree. It decelerates to rest in this amount of time. How much force is, that should say, exerted, not entered on the car. Anytime you see a problem that involves changing of velocities, mass, and a time, that's going to be an impulse problem. If you see masses and changes of velocities, you're looking for forces, and you see displacements, that's going to be a work energy problem. But if you see times, it's going to be an impulse problem. So I rewrite my main impulse equation, force times time equals change in momentum, and now I begin to substitute in. Of note here is your final minus your initial velocities. The final velocity, since you're hitting the car, is 0, or hitting the tree, is 0, while your initial is 30, so you have 0 minus 30. And so we find the force that the tree exerts on the car, negative 140,000 newtons. Negative because it's going the opposite direction the car is going, and I called the car's initial velocity positive, so the force going the opposite way negative. Of note, that is not the same force that the person inside the car experiences. One, the person's mass is a lot less, so not as much force is needed to stop that person. And two, we can actually, using seat belts, airbags, etc., cause the collision for the person to take a longer time, allowing the person to slide forward a little bit out of their seat towards the steering wheel. That's a further distance to go over, thus we can allow less force to be exerted on the person. Now let's go ahead and work an elastic problem. So here I've got an 8-ball, a cue ball. Cue ball is going to strike the 8-ball. I'm going to call my cue ball object number 1, and I'm going to call my 8-ball object number 2 in this elastic collision. Since I notice the two objects bounce off of one another, or another way to think about it is, since they don't actually stick together, I must use the elastic equation, where everything is separated out from each other. And the goal is, how fast is the 8-ball going to end up going after the collision? So I'm going to look for this final velocity, and I know everything else, so all I need to do is start substituting in. As you can see, the momentum for the 8-ball, which is at rest in the center of the table, is going to end up being 0 there, allowing me to solve for the final velocity of that 8-ball. And the momentum of the cue ball is decreased. Initially, it has a velocity of 1.2, and after the collision, it has a velocity of 0.25. So now I just subtract the 0.2225 to the other side and then divide by 0.78. And I end up with a final velocity of 1.0839, blah, blah, blah. So that's 1.1 using our two significant figures given to the problem, 1.1 meters per second. The next problem chaining off of that is going to end up being a work energy problem. If the pocket is 1.3 meters away, notice that it's giving me a displacement, not a time. So if it was a time, I would be thinking impulse. Since it's a displacement, I'm thinking work energy theorem. And the coefficient of friction is 0.1. how fast will the 8-ball be going when it reaches the pocket? So the ball starts out with some kinetic energy, the 8-ball rolling towards the pocket, and that energy is going to go to two places, work done by friction and then the kinetic energy it ends up with whenever it gets to the end. Go ahead and change force of friction into mu times normal force, and then you get that normal force, remember, from the y-axis. Well, since this is a flat surface, I don't even need to do a free body diagram. I already know that normal force is going to equal the force of gravity, mg. Notice that I have an m in every term, so I can cancel those out, divide both sides by m. Solving this around in letters, I'm going to subtract mu g delta x over to the other side, times both sides by 2, and then I'm going to purposefully go ahead and distribute that. And of course, finally, square root both sides. And as you can see, whenever you plug in the numbers there, you're actually going to come out with a negative number underneath the square root, an imaginary number. And that's because the ball apparently never reaches the pocket. It would be imaginary for it to actually get there. So the final velocity, it doesn't exist how fast it's going to be going at the pocket. It never reaches it. That's something that happens sometimes in problems. Please pay attention to what's going on in the math, and you'll actually recognize things that the problem's asking for one thing, but in reality, it never actually does occur. Now let's do a couple of inelastic collisions. That's where things stick together. We're going to make these perfectly inelastic so they completely stick. Here I've got a basketball player training, and her coach throws a medicine ball towards her. It's 6.85 meters per second. It has a mass of 5 kilograms. She has a mass of 65 kilograms, and the question is, how fast is she going to end up moving backwards? So since they stick, we use the inelastic. I'm going to call the girl object 1 and the medicine ball object 2. Notice also I'm calling to the right positive, to the left negative, so the ball is moving with a positive velocity, and the girl in the end, the girl and ball together, because she's going to catch it, is going to have a positive velocity also. Backwards reference to the girl, but I'm calling that way positive. And I end up with a final velocity of 0.49 meters per second squared, 2 sig figs because of this mass here, even though I have 3 here and 3 there, 2 sig figs, that initial mass. So she's going to move backwards at 0.49 meters per second. Going to run through the next problem very quickly, but basically I have a train car moving forward and some coal is being dropped into it. Now, the momentum of the coal, even though it's moving downwards, the downwards component isn't going to factor into the conservation of momentum. In fact, I'm only looking at the conservation of momentum left and right, if you will, and I'm going to call to the right positive here and to the left negative. So the coal's initial momentum, and I'm going to call the coal object 2 and the train car object 1. So the coal's initial velocity is going to be 0, making its initial momentum 0. So this is an odd idea. Whenever you add mass into something, it's actually sticking on. Even if you're just dropping extra mass in, it's an inelastic collision. And working the quick math, come out 2.4 meters per second. Lastly, a couple of explosion problems. For example, recoil of a rifle. If a rifle, given mass there, fires a bullet, be careful, that bullet's mass is in grams. Forward, how fast is the rifle going to recoil back? Now I can recognize this is an explosion problem because the two objects were initially at rest. They were together. That's the key with it. They were together, and then they separate out through some means here. So now my explosion equation, substitute in. Now the negative sign in an explosion should make sense. That's indicating direction, right? If I'm calling the direction of the bullet, notice that velocity is positive, then the final velocity of the gun should be negative, coming back this way. So by definition, I'm calling this way positive and that way negative. Notice the positive sign on the velocity here. Also of note is converting from grams to kilograms. And I come out with negative 1.8 meters per second, negative because it's going backwards, 2 sig figs because of the mass of the rifle. And I'm working these problems with numbers, although it could be very good to work with letters. These are very, very simple, straightforward problems. Now this last problem is somewhat of a hybrid. The boy and the ball that he's going to throw are already combined at the beginning, so it is an explosion, but they have an initial velocity. They're already going 3.5 meters per second. And then the boy's going to throw the baseball, or whatever ball it is, that is, and we're going to see how fast the boy ends up going. Now obviously whenever he throws it, it's going to slow him down somewhat. Now, there are two ways to solve this problem. It's all about what's your frame of reference that you end up looking at. Here, I'm considering my frame of reference to be the ground, or my point of reference to be the ground. So they're actually already moving here in the beginning. I have an initial velocity times their mass, because they're two things stuck together, kind of like the final side of the inelastic problem. It's just now it's on the initial because initially they are stuck together. Equals, now they're going to separate. Stuck in the initial, separate in the final, which is opposite of the inelastic equation. If you wanted to solve this just as a standard explosion, you would talk about relative to the skateboard or relative to the boy, as opposed to relative to the ground. But I like solving things relative to the ground. Now I'm going to call the boy object 1 and the baseball object 2. And with two sig figs, I come out with 3.1 meters per second. All right, I hope this video was quick and a good review for you. We'll take it up probably another notch in class.